Lesson 05 has two objectives. We're going to piggyback off some ideas that we did in our counting methods, but we're going to continue on with that and expand that idea to do two things. To calculate the theoretical and experimental probabilities, and secondly, to compute probabilities of compound events. So this is about calculating probabilities, not just simply counting how many events can occur. So if we look at some of the definitions, some of the ideas, background information on this lesson, first thing is getting the idea of what probability is. Probability is the measure of the chance that a given event E will occur. We're going to figure out what are the odds, what are the chances that it's going to occur. The probability, and it's represented as P at E, so the probability that a certain event occurs is represented by this symbolically. And that's the probability the event will occur, and it's always given between a ratio of 0 and 1. If you get a probability event and it's equal to 0, that's saying it's certain that it will not occur. The best you can do is you can say it is certain to occur, and that's when your probability of an event is a 1. So a 1, if you want to think of it this way, is 100% guarantee that it's going to occur. And anything in between there is your chances of that event occurring. So the lowest chance that we can have is 0, and the highest that we can have is 1, and that's the ratio of the favorable outcomes to the total number of outcomes. So we're also going to talk about a few more background pieces of information before we go into an example. It says a probability model is a mathematical model used to represent the outcomes of an experiment. A uniform or simple probability model is used to describe an experiment for which all outcomes are equally likely or have the same probability of occurring. This is important in our models when we think about when we're studying these. We want to make sure that each outcome is equally likely. If one outcome is weighted more, where it may more likely happen, we got to use a different model. So we're going to be looking at and exploring these models where every event that we try to have happen will have an equal probability of occurring or equal chance of occurring. Now the last little bit here, and then we'll kind of get into more of our structure of it. If we assume that all outcomes of an experiment are equally likely, then we can calculate the theoretical probability. Theoretically, we're saying this is what should happen, that event will occur using a sample space of possible outcomes. We could also calculate the empirical or the experimental probability, which means we're actually going to conduct the experiment ourselves, record our results over several different trials, and then calculate how many times did our event occur. So we've got the theoretical is what should happen in the long run. We've used terminology like that before. If we look at the overall long term, if you do this thousands upon hundreds of thousands or millions of times, this is what our experimental probability will get closer and closer to. So there's two basic concepts here. They got theoretical and experimental. When you think about theoretical, that's what the long run, that's what we think should happen in the long run. And the experimental probability means that we're actually going to conduct the trials, and we're going to take the information that we got from our trials or experiment and use that data to try to calculate the probability. So they look very similar. If you look at the key concept, if we want to find the probability of any event happening, we want to figure out what's the number of favorable ways an outcome can occur. They call it the favorable outcomes. How many instances can we win, or can we find something that's favorable, over the number of possible outcomes? How many outcomes are possible in the entire experiment? The only difference on the experimental is we're actually going to run the experiment, and then we're going to count the number of favorable trials, how many things came out the way we wanted to versus the number of trials. So let's take a look at our first example. It says the graph shows the results of several trials of an experiment in which a single die is rolled. Now, a die is like a number cube. What is the experimental probability of rolling a 6? Now, an experimental probability says we must use the data that they give us, so we've got to look at the data that they gave us in the chart, and we are seeing that if we roll a die several different times, we can figure out how many times a 1 came up. So looking at our table in our graph here, what we know is that when we rolled this die, we came up with 9 times it rolled a 9. 9 times we rolled a 1. And then we rolled a 2 6 different times. We rolled a 3 12 different times. And we rolled a 4 6 different times. We rolled a 5, that looks like a 7 different times. And we rolled a 6, a total of 10 different times. So from this, we can figure out what the total number of times that we did this experiment. So we're going to first of all figure out what's the number of trials that we did. So I know I ran 9 trials because I got 9 1s. We ran 6 trials because we had 6 2s, and so on. So we got 12, another 6, a 7, and a 10. So if we do the sum of this, we can figure out what the total number of trials is going to be. So 9 and 6 is 15, 15 and 12 is 15, 25, 27, 34, 44, and 6 is 50. So you can double check my mental math on that, but we ran this experiment 50 times. So what we're doing is we just figure out the number of trials that we just rolled. Now to calculate probability, what we want to do is we want to figure out what's the probability according to our question that we will have rolled a 6. So I'm going to put a probability of 6. That's our event that we want to have happen. So we know that we ran 50 trials. Now we want to figure out what's the number of favorable trials that we had. So we're going to go back to our table and we're going to look at our table and it says we had 10 favorable trials. 6 was a favorable outcome, so it's 10 out of 50, which reduces down to 1 out of 5. And if you like it as a percentage, then you can look at that and say, well, that's 20% of the time we roll a 6. So that is the experimental probability. Now the second question, the part B, is what is the theoretical probability of rolling a 6? Well, there's just a slight adjustment in our thinking. All we're going to do is we're going to switch the model over here where it says the probability of the event is the number of favorable outcomes to the number of possible outcomes in theoretical. So let's take a look at how we're going to adjust to this. There we go. So the probability of a 6 in the theoretical model is saying, okay, you've got a number cube, and the number cube has 6 different sides. What's the probability that you'll be able to roll a 6? Well, there's only one favorable side out of the total number of sides, which is 6. So here's what I'm looking at. There's only one favorable outcome on a die, but there are 6 possible outcomes on it as well. So that fraction is already in lowest terms. So if you want to convert to a decimal, you simply take your 1 divided by 6. I don't know that one off the top of my head, but that's a 16.666%. So if we do the rounding, it's 16.7% chance. Now, we should see values that come back fairly close to each other because the theoretical should model what the experimental data should get closer and closer to in the long run. We keep running these trials longer and longer periods of time or more trials. So we're making a distinction between how to calculate probability in experiments and trying to calculate the probability in a theoretical model. But basically, we're just calculating probabilities. How many favorable outcomes versus the number of possible outcomes.